Hello guys, I'd like to do a little video on basic proofs of area. So what this is like if you went to a math class or something like that and you wonder, how is this all derived? Well, we'll start like at the basics first because it's interesting how it works its way up. But this is just focusing on triangles and squares. So, you know, let's take for example a real life situation in which, in this here, in like an assembly hall or a arena, you see how all the chairs are put into like, shall we say, a square shape, and all the chairs are equally spaced from one another in terms of the rows and the columns. And what happens is you can derive the area from using this, basically using a practical world example in maths, so we can derive it from there. So let's do that then. Like say for example you want to I'll go back to the chairs again. You want to work out how many chairs is in that in that block. Do you want to count every single chair, or do you want to get away with a certain shortcut? Well, yeah, there is actually a shortcut. So if we take, for example, a square, an equal size square with equal length, so this is the same as this length here. So let's draw some chairs. So I'll do it in like a greeny colour. So that's one chair. That's 2, 3, 4, 5, 6, 7, 8, 9. Now, what you see for there, all the chairs are. You can tell there's 9 chairs, but what's an easier way of doing it? Well, we can take the fact that there is 3 on this length here, and there's also 3 on the other length as well, which is this here. And you notice that if we multiply the number of chairs here on the top with the ones perpendicular, including the one that's on the edge for both, you can get the number of chairs in that square. So we know there's 9 chairs, so 3 multiplied by 3 is 9. So yeah, so we can put area equals 9. Or 9 meters squared, or 9 kilometers squared. It depends what you're working with, what units and what. And you can just use chairs, like 9 chairs. That's 9 chairs. That's the area. But what, for example, if you want to work out a triangle? Well, we can do that, actually. We could easily just count the number of... So we could easily just count the number of... is this working? Yeah. We could just easily count the number of the chairs and the half of chairs and stuff. So if I do that properly, so if we can notice that there's 3 here, and there's half of these. There's a half a chair there's 3 half of chairs along this line here where it cuts off. So one half, 2 halves, 3 halves. 3 halves is 1.5, and if we add the remaining 3 seats here, that's 4.5. So we know that is, oops, it doesn't matter, I guess. It's 4.5. So there you can see that when you do a triangle, it halves the area of the full square of what you were dealing with. Right, so there's 4.5 chairs. But how do we know that what about more complicated squares and triangles? Does the same principle work? Yeah, to a certain extent. So if we get another weird, shall we say, so we get another like square, but it's not going to be a square as such, it's a rectangle. So it's got one of the lengths is greater than the other length on its perpendicular side. So we know though the difference between this rectangle and this square, this perfect square here, the lengths on all the sides are the same, but here there's only two lengths which are the same. Basically, the rectangle has two different values attached to it. So this and this were the same, but this and this will be the same, but this and this length will be the different. So we can say, for instance, let's get the chairs again. So let's say 1, 2, 3, 4. I want to make this work. 2, 3, 4, 5, 6. Again, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then 1, 2, 3, 4, 5, 6. Yeah, so there we can see. If we use the same example again. So how many chairs are here? 1, 2, 3, 4, 5, 6. So 6. So put 6 here. And how many chairs are here? 1, 2, 3, 4. So 4. So using the same principle we use this perfect square here, we can 6 times 4 equals 6, 12, 18, 24. So the area is 24. So area is 24. 24 chairs, 24 meters squared. But I bet you're wondering, like, is there 24 chairs? Or if we count them all individually? Well, yes, it is. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So there's 24 chairs altogether in that rectangle, which further proves that if you multiply the chairs on one side and the other, you get the number of chairs. So, but what about with a triangle? It's a bit odd, isn't it? So if we get an example, say if we stick a line through here. Now, yes, we could say half of the triangle is 12, but it's very difficult to count all the chairs individually. So, for example, or by different fractions, like so, we know 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we know there's about 10 chairs within the triangle so far, but now we have to count all the ones that are in the boundary. And I'm probably mistaking you there, actually, because maybe this one is in that one. I'm probably counting that one as well, thinking it's safe when it's not. So it gets confusing when you have to basically count all the individual fractions on the triangle. So how can we prove that the number of chairs is half the number of chairs is equal to, as a triangle, is equal to the half of the number of chairs on the rectangle? And it can be done. So if we take the same square again, so if I'm going to undo some stuff. So if I get, so it's 6, so actually no, I'll split it. So if we split it like that, now, and we count the number of chairs. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's 12 chairs. So there's 12 there, and there's 12 there. So we know that half of 20, half of that rectangle is 12 on each side. Now, if we say, for example, this whole length here is, shall we say, X, and this length here is Y. So if we split the rectangle, what we're doing, we're splitting X. So basically what it ends up being is half X and half X. And we know from our previous examples we just discussed that if we multiply the number of chairs here by the number of chairs here, we get the area. So because after we've halved the rectangle, if we do half of X multiplied by Y, that is the area of half of there. So yeah, so half of the area of that full rectangle. So yeah. So what about, so now with the triangle, let's do it with the triangle. Now the triangle, we're saying half, aren't we? Half of Y and X. Well, essentially it means the same thing. So yeah, X is full X and Y is full Y, but because we're having the whole thing, basically it comes out the same thing. So half of X multiplied by Y equals half of A. So yeah, half of XY is half of A. So yeah, there we go. We've just proven that the triangle. So if we sum it all up, we can say for certain that for a rectangle or square, the area is A times B. So A is one length and B is the length perpendicular for it. For a triangle of the same square, area equals half A times B. Yeah, so yeah, there we go. So yeah, this is pretty obvious. This is very obvious because it's like, this is what you taught at basic math. But it's good to know how real world situations influence the math we love and know. Questioning love. You know, not everyone loves it. It's a bit of an odd subject. It's a bit complicated subject. I know, boy, yeah, it is. But yeah, it's good to just look at real world situations, how we derive our mathematics from it. It's not just imaginative. Well, it is in a sense, but it's not. It's real stuff that has an impact on the world. So yeah, I hope you enjoyed this video, and we can further derive from this and work out even more complex situations like Pythagoras. How do we derive that? Or trigonometry, how do we derive that? And we can look in further videos. Okay, you take care. Bye.